Hello
Okay, so
everyone. I am very excited for the first ever student talk at OMC. Thanks everyone for joining, and I'm so happy that the first talk is taken by Samvar. He's an amazing teacher, and I'm so excited for to hear him talk. So also I was saying this earlier. If you have any questions about the Informatics Olympiads, or so you've probably seen somewhere already on the server with the chess tournament and everything. But he is a very excellent informatics Olympiad enthusiast, and yes, he has done very prestigious programs like Promise, which most of you might know about, and also the program in algorithmic and combinatorial thinking. And he will be talking about one of my favorite topics, which is graphs today. Um, Also, feel free to ask him about any questions you might have about ZIO or SETSIO or any that sort of a thing, or code courses. Somewhere over to you. Thanks so much for doing this.
thank you so much for the very kind and thanks so much for the introduction. So yeah, as I was saying, graphs is one of my favorite topics as well. Okay, it is my favorite topic, period. So I'm really happy that I have a chance to, discuss it with other people. So yeah, without further ado, let's begin what I hope will soon be your favorite topic as well. So yeah, graphs. So the thing about graphs is, before I start, it's something which is not pertain to a specific field. You can study it from a mathematical point of view. You can study it from like computer science and programming. It has applications in other fields as well, like science and AI and machine learning. It's literally universal, and that's something I really like about it. But the viewpoint with which we're going to look at it today is through computer science and math mainly. So I think there was already a previous lecture on the basics of graphs, and it was quite an amazing lecture. So I'll do a quick recap of some of the basic terms and what graphs are, and then we can move into graph algorithms. So does that sound good?
Yes.
Okay, so guys, feel free to either unmute and ask your questions or just message in the chat. Anything works. And please, let's keep this interactive. So I'll be asking questions. You can unmute and answer. And any doubts you have would, everything works. Okay, so let's start. So what are graphs? A graph is just two sets. For all that it's been talked about, at its very core, a graph is two sets. One is the set V and the other is the set E. This is the set of vertices and this is the set of edges. So what it means is that if we are given these two sets, V and E, we can build the graphical representation as we think of it from these two sets. So suppose I'm given that V is 1, 2, 3, 4, 5, and that E is 1, 2, my bad, 2, 3, and 1, 3. Then this would be 1, 2, 2, 3, 3, 4, and 5. So from these two sets.
Are you talking about directed graphs? Are you talking about directed graphs or normal graphs?
Yeah, so I'll get into types of graphs, but this is just a basic undirected graph here. We'll get into that in a minute. So as you were saying, there are different types of graphs. We'll get to that in just a second. So from this set, these sets, you can get a graph, and from this graph, you can also build this set. So now, as I think Aritra was saying, graphs are of different types. So there are different ways in which they can be distinguished. One is on the basis of the direction of the edges. In this case, you have directed graphs and undirected graphs. And as the name might suggest, the only difference between the two is whether the edges are directed or not. That just means that if you have an arrow, that means it's directed. This means that there is an edge only from 1 to 2 and not from 2 to 1. So if we take my favorite example, where each of these are towns and the edges are roads, you can get from 1 to 2, but not from 2 to 1. It's like a one-way street. On the other hand, if it was undirected, then you would just have this, and it would mean you can go from 1 to 2 and from 2 to 1, or from 2 to 1. Both are possible. So if you have direction on both edges, it's the same as being bidirectional. This is bidirectional. And if all the edges of the graphs don't have arrows or direction, then the graph is termed as undirected. Otherwise, it's termed as directed. So this is one way in which graphs can be distinguished. And the second is something called weighted and unweighted graphs. We'll come to that a bit later. So right now, we can just keep it as if you have an edge from 1 to 2, directed, sure, or let's just keep it undirected for simplicity. And if you have an edge from 2 to 3, apart from where they're starting and ending, there is no difference between the edges. There's no extra parameter like cost or time or nothing like that. It's just where I start, where I end. That's all we're dealing with edges for now. And we have this one parameter of direction. So does that clear what basically graphs are? If there's any doubt, please feel free to ask.
Yeah, that's clear.
Okay, awesome. Okay, so then let's start with graph algorithms. So, no doubt. Okay, awesome. So the main reason we have graphs, these graphs, it is a structure which helps us analyze data. So we can term these sets as data because you have some amount of information like towns and roads. Well, this graphical representation seems to be something which can be analyzed a lot easier. But when I say analyzed, what exactly am I saying? What can we do with these graphs? Well, that's what we will see through the algorithms, which we'll be covering now. So graph algorithms.
One more thing, like in this, we are dealing with simple graphs only or both?
Yeah, we'll be dealing with only simple graphs. And okay, so yeah, that's a good point that you pointed that out. So one, we will be talking about only simple graphs, and second, there'll be no self loops. I think that's covered, but yeah. So for each edge, it won't have an edge to itself. And between any two vertices, there is only one edge of the same direction allowed. I think that covers the definition of simple graphs, right? Yeah. So yeah, we're talking about simple graphs. Yeah. So for graph algorithms, most of them cover, or some of them, at least in the beginning, talk about something which is called a traversal. So a traversal is a path or a movement through the vertices of the graph via edges. So it's something like, if I go back to this example, I can go from 1 to 2 to 3 and back to 1. That path we take is something which we can call a traversal. And as soon as you think of a path or traversal, the first question I at least got was, can we find the shortest path? Can we find all paths? Can we prove there exists a path? All these are questions which you immediately get when you think about traversals. And these are the questions we'll try to answer with the help of graph algorithms. So should I start off with graph algorithms? Yeah. So I will actually be covering graph algorithms with an example and then formally defining how the graph algorithm works. So we'll be covering two graph algorithms at the moment, BFS and DFS. Both of these are called traversal algorithms. Yeah. So, okay, so let this be a graph G, this entire thing. This is my graph G. Okay, this is my graph G. So the vertices are S, A, Y, D, X, C, B, etc. The edges are S, A, S, Y. So just to ensure that everyone has understood, could someone tell me, is this graph connected? Sorry, is this graph directed or undirected?
Undirected.
Undirected. And what if I do this?
It's still undirected.
Every pair of edges, I'm going to add direction in both directions. Is it now directed or undirected?
It's undirected because you're adding for every pair.
Would anyone like to agree with that or disagree with that?
I agree.
So we're
I
getting
I also
I
agree.
mean, even without the arrows, you are doing the same function of coming, going, and coming back. So it does not matter.
it does not matter. Okay, I agree with that completely. It does not matter. Okay, that's the word choice is harsh. Instead of saying it does not matter, I would say it does not make a difference to the movement. But is it the same?
No.
Yeah, you're right. It's not the same. So for the purpose of this class, this will be called as directed. It's called bidirectional because you have edges in both directions. We'll call this directed. But for all intents and purposes, it is undirected in its functionalities at least. But I'm just trying to draw a line that if there is direction, we call it directed. It doesn't matter if the direction is in both ways, in one direction, in no ways. If the parameter is called upon, if the parameter of direction is involved, the graph becomes directed. Does that make sense?
Yes.
Okay, cool. I've got a question. What is BFS and DFS? We'll get to that in a minute. That's what I'm going to explain now. Yeah, so since there's no point of adding the edges as people were saying, we'll consider this undirected graph. So now let's explain what traversal is. So suppose I'll choose a different color. Yeah. Suppose I take this vertex S as my main vertex from where I start all the journey. So you can think of it like all of these are towns and all of us are in town S. And we want to figure out which towns we can go to from S. So intuitively, if you are given this situation of a map, a graph is similar to a map, what would you do? Would someone give me what their idea is? How I can figure out where I can visit? From S, using these edges, where all can I go?
Traverse every possible edge and mark the cities which have been visited on a list, maybe.
Yeah, very nice answer. But you use the word traverse while I'm trying to define what traverse means, right? So do you want to give defining
So we
traverse?
will use walk, I guess, walk through the edges.
Walk through the edges. Yeah. Any other answers? All these answers are correct, by the way. Any other?
Move from one vertex to another until we cover every single edge.
Okay. Now that answer is interesting. I'm going to write that answer. Move until all vertices are covered. Does anyone see a problem with this?
Yeah, the graph is not
Graph
connected.
isn't connected.
The graph is not connected. Very good. So if you try from S, you can never ever reach E, right?
Yes.
Yeah.
If your graph is connected, then your answer will work. You can just move until all vertices are covered. But in this case, it's disconnected, so that wouldn't work. Okay, so most of the answers which I got was move or traverse or walk. How will you do it? How will you walk? Give me the example. I'm at S. How will I walk?
If there's an edge connecting S and some other vertex, we can just like move from S to the other vertex.
Okay, sure. So move from S to A, move from S to D, move from S to B, so on and so forth. You keep moving on the path until every vertex is covered, right? So intuitively, yeah, that's what we do. I'll just try to explain it a bit more formally. So let's start. So I'm at S. I see that I can go to A, I can go to B, and I can go to D. I visit all three, right? So this is visited, this is visited, this was visited. I visit A, B, and D. Now I'm thinking, okay, I'm at A, I'm at B, I'm at D. Where all can I go? So A says, okay, let's take B just simply. B says, I can go to C. And then C says, oh, I can go to Z. This is what we would intuitively do. Am I right?
Right.
But unfortunately, when we look at it from a computer science point of view, this is not optimal. The reason it is not optimal is that what you're going to do is basically brute force. You're going to try every possible way of reaching all the vertices. And that is correct. It's not a wrong way of traversing the graph. It's just not optimal. When we look at it from a computer science point of view, you try to minimize the number of operations. When you try to minimize operations, you try to look for the most efficient way of traversing the graph. So what we actually do is this. So we say, okay, from B, I can go to C. Very nice. But there were two more people here. There were A and D, which were still left. So from A, I can still go to Y. And from D, I can go to X. Now this entire layer is, okay, yeah, better go on.
Yes, but wouldn't just taking one and then pursuing that and then coming back, wouldn't that just be DFS?
Yeah, it is. I'm just trying to explain BFS now and then go to DFS to show the contrast between them. You're not wrong. You're not wrong. Yeah. But okay. So just for 2 to 3 minutes, forget about what Bhairav said. It might confuse you. So let's just continue with what I was saying. So from A and D were still open at that point. So I can go to Y, and from D I can go to X. Do you see how this covers layer by layer? A, B, and D were all at distance 1 from S, right? Distance 1, distance 1, distance 1. While Y is at distance 2 from S, X is at distance 2 from S, and C is at distance 2 from S. So I'm covering this entire layer. And then when I go to C, I will go to Z, which is distance 3 from S. So we're covering layer by layer, or what we call breadth. I'll explain why we use the word breadth in a second. But do you agree that this is a valid traversal, first of all?
Yes.
And does anyone want to take a shot at why I use the word breadth?
Perhaps because of the
Like,
of each path, assuming that they're all equal, but it shows different standpoints. How many different standpoints you have?
I didn't quite understand. Can you repeat?
Like B and like from S and Z, we have B and C. So it's kind of like showing how many steps you can take if you can count going from one town to the other as one step.
Sure, sir. That's not wrong. Yeah. But what is so unique about the word breadth? I'll only answer maybe. So what breadth means is width. It means like wide. What that means is, do you notice? Okay. Sorry. Was the term neighbors defined in the previous graph class? I'm pretty sure it was. But can you just confirm?
Yeah, adjacent, I guess, is defined if the shared image.
Yeah. So the neighbors of S here are A, B, and D, right? So do you see how we first cover all the neighbors of S, then we cover the neighbors of A, B, and D in that order. So we go Y, C, X, and then we cover the neighbors of Y, C, and X, which is in this case only Z. So we're going in a breadth first manner.
But
And
how how is this more optimal than the previous thing you did? That's the same, right?
Okay. So as you and both Bhairav are saying, okay, I'll come back. I'll come to that in a second. Just give me a second. Okay, but do you just understand how this is breadth?
Yes.
yes.
Awesome. Now coming to what Bhairav was saying and what Aryan, I think what Aryan was saying.
Yeah.
Yeah, okay, cool. So what they were saying is, well, when I went from S to B, why would I go to A and D? Let me just explore everything I can from B. Okay, from B I can go to C. Wow. From C I can go to Z. Amazing. Okay, but there's nowhere to go from C. From nowhere to go from Z. So I come to C. Oh, I can go to D. Very nice. Now, is there anything else I can do from D? No. Is there anything I can do from C? No. Let's go back to B. Oh, okay, nothing to do from B. Now let me go to S. Oh, I can go to A. Very nice. From A, I can go to Y. And this is also a valid traversal, right?
D2x you forgot.
Sorry, D2X, you're right. D2X, and then this is a valid traversal, right?
Yeah.
Yes.
So was depth. Now I think this will clear what I'm still going to answer your question about optimality, but this is depth. You go as deep as you can into the graph. You go S to A, S to B to C to Z, and then you just recurse, move back, and cover the other possibilities, right? So there's a difference between breadth and depth. Makes sense?
Yes.
Okay, awesome. So now coming,
Yes.
both BFS and DFS are same time complexity wise. There is no difference between them. The algorithm which you meant to say was DFS, and that's correct. But the way you said it was, let me cover every possible edge to cover all the vertices. This ends up becoming an inoptimal solution because I would cover vertices. I would check stuff like, okay, let me just add a edge so that clears it up. Let me add C to Y. In your algorithm, you would check C to Y, while in BFS and DFS, you don't check C to Y because C to Y is not in the tree, if that makes sense. So what you said, your idea was correct. DFS and BFS are both equally optimum. Just the way you said it was inaccurate. Does that make sense?
Yes.
Wait, so optimal means that the number of ways you are traversing the entire graph, right? Or the number of moves.
I will get to what. Okay, so you can think of optimum being that they cost me the same amount of money. I will get to how you figure out what the cost is in some time.
Okay.
But it's like it costs me the same. BFS and DFS are equally good. Equally good is the word I would use. So does BFS
And are they the best or there is something?
for traversal of, okay. So it depends on what the question you are answering here is. In the case where you have a undirected or a directed graph and you just want to traverse it, yes, BFS and DFS are, I think, the best. There might be some really crazy optimizations you can do, but those are like really, it reduces by an infinitesimal amount, and the amount of work you need to do that is just too high. So they are basically the best. Yeah. Yeah, I think someone's unmuted.
Okay.
Is there any other question? Okay.
No.
So I'll just go over pseudocode really quickly. And this is how you would write the algorithm. So let's start with DFS. So if you noticed in this graph, we started from select vertex S. But instead of S, if we would have started from, say, Z, then you would have had a completely different tree. Am I right? This is a tree, by the way. These two are trees.
Yes.
Am I right? Yeah. So if we perform a graph algorithm, one of its parameters is the graph itself, and the second is the starting point, or what we call the source. And I will get to these four vertices in a bit. Like, okay, I'll actually just explain it now. So when you did DFS from S, since there was no possible way to reach E, F, G, or W, it's just not going to be in the tree. You can't reach it through a traversal, so it's not a part of.
Wait, which one did you tell was a tree?
Both of these are trees. This is called the BFS tree, and this is called the DFS tree. I will.
No, means, do you mean that the graphs are the trees? Because I don't think so. The graphs are trees because SDCB is a cycle.
Sorry.
SDCB is a cycle, right? So how are the graphs the trees?
Very good question. The graph, this graph is not a tree. You are absolutely right. But this representation is a tree. When you perform BFS on it, the resulting transformation gives you a tree. This graph, G is not a tree, but this is a tree and this is a tree. If that makes sense.
Right.
In
So
the
look at those transformations as the graph itself.
Yes, exactly. And I will formally define trees in, I think, 1 or 2 slides. So if you didn't quite get what this was, don't worry. I'll come back to it in about 5 minutes. So
in the DFS, why do we actually have to connect A to S?
okay.
Can't we just connect C to Y and then Y to A? I mean C to A.
Are you talking about DFS or BFS?
DFS.
DFS tree. Okay. So you're saying, why do we have to connect S to A? what can you do instead?
C to Y and then Y to A.
Right. So C to Y was added so that I could explain the inefficiency of brute force. In the normal graph where we did DFS, C to Y did not exist. But you are right. If it did exist, you would do C to Y, and that would be how DFS works.
Okay.
Yeah, awesome. Those are really good questions. So moving on to how DFS works, I'm going to write the pseudocode quickly. So what we do is we check if source is visited. Source is visited. Then we just return. There's nothing to do. You've already reached. Visited means that you've performed your traversal from that point. So this is like a trivial base case. This is like when you stop. Because you'll reach a case when everything is visited, right? At that time, if you don't have this, you'll go into an infinite loop. So what we do is, for each, so okay, first mark source as visited. Then for each neighbor, if not visited, DFS on it. Okay, I'm sure people will have doubts if you've not seen pseudocode before, but I don't know, maybe I explained it nicely and you understood.
It's like recursion you're doing.
It is recursive, you are right. So does it make sense, or should I explain?
Yeah, it makes sense. So.
Okay, so if it makes sense, can you tell me what is the importance of this line?
Of if not visited, yeah, if not visited, it's like it's not, it cannot be the source because source is marked as visited, so we can just apply DFS on it, I guess, like this.
That just prevents us from going into an infinite loop.
Yeah.
Or that induces the recursion.
Say, but Adarsh's answer is correct. If you did not have this line, you could end up just doing this. Just going back and forth, back and forth, back and forth, back and forth.
A self loop, like that.
Yeah, just keep doing that from A to B, B to A, A to B, B to A, so on and so forth. So it just prevents you from going into an infinite loop. Yeah, Bhairav, go on.
Actually, because you already put the if source visited return at the start, if it has been visited and you go DFS on it, it just comes back.
Good point. Yeah, okay. Wow, I managed to prevent an infinite loop myself. But it'll still not work, right? You do realize that the DFS will not happen completely. Because it'll check that it's visited and it'll just return. It'll stop at that point. If there was some other traversal left, it would stop that.
No, it would, because you already put at the start, it would only close that instance and the others would still be there. So then it's effectively the same.
Fair enough. See this, DFS on A. DFS on A. A will become visited. I will go to B. B is not visited. I'm going to go back to A. A is visited. I'll return. My DFS to you is A to B.
No, it will, but it will only, I guess it will only return the one which is at A, the newest one. So then it will go back to B and then B will go to C.
Yeah, that's dependent on your implementation, by the way. If you've implemented it in a way where you have your colors and parent and all that, then you are right. But in this implementation, like in a programming way, return would just mean stop the function, which would mean that you would just exit it.
Okay, I have one more question, that if like this is DFS, the same code works for BFS also, then how can you differentiate between the two for
Last question. Will the same code work for BFS? You tell me.
No, it won't. Because
It
BFS is something like the shortest length from the source.
Excellent. But okay, can you explain it slightly differently? What will change from this and BFS? I'm not asking you for the code of BFS. I'm just saying, like, DFS does depth, Well, BFS does something else. What does BFS do?
It's
From the
looking
source,
at the layers. So like the code is whole different. Everything will change, no? Because we are talking about layers like neighbor. We have to define neighbors for the.
Yeah, very good. That's absolutely correct. So I'll just explain it. What this code is going to do is, if you have something like this, what the DFS code is going to do, it's going to go from here to here, then here to here, then here to here, then here to here, then here to here. Then it will come back and visit these two. But what BFS would do is, it would first check all three of these because it does breadth, and then it would move down. So the code cannot be the same. Does that make sense?
yeah.
Yes.
Okay. So I am contemplating if I should give the pseudocode of BFS or not, because it involves a lot of computer science stuff like queues and stuff. Okay, I'm just going to do it. So the difference between BFS and DFS is depth versus breadth, as I'm sure you understood. So what BFS does is it goes layer by layer. What it does is it initializes something called a queue, and the queue just consists of things which it wants to visit. Now, I'm going to keep this very simple. And if someone here is a computer science guy, please forgive me for not explaining the beauty of queue, but I want to keep this mathematical. So what it does, it pushes the source, it visits the source. So what it does is, so you push the source into it, and then what it does is it pulls out the first one. So it does q.pop. Pop just pulls out the first, like the topmost thing. And then what it does is for each neighbor, q.push, if not visited. Now this may seem the exact same, but the difference is that in the previous case here, where we had for each neighbor, what we were doing is we were running DFS again. So it would go neighbor to child to child to child to child and so on. But when you use this push thing, what the pushing will do is it keeps everything in the first layer. It will cover all of these, then cover everything in the second layer, then cover everything in the third layer, and so on. If you didn't quite understand the implementation, it doesn't really matter as long as you understood the idea of BFS.
What if two from the first layer are connected to the same one in the second layer? Then like which one will be connected to which in the BFS?
Yeah, you're saying you have S, you have A, you have B, you have C, right?
Yes.
So BFS will go S to A to B, right? Breadth covered. Then arbitrarily, depending on how you have implemented it, it will either take A or B and do this. So this and this are both possible outputs. Both are valid BFS trees. You can have multiple BFS trees.
Okay.
Does that make sense?
Yes.
Very cool. So this is BFS and DFS, the basic idea and implementation. Does it make sense to everyone?
How
Yeah.
do you define push? I didn't understand that part.
Okay. So, okay. You know what? I'm actually going to take this after the class because it's purely for coding. If you want to implement this using like C++ or Python or something, then you would need what push and pop is. So I'll take it after the lecture if that's okay, because I want to keep this like mathy.
Yeah, no problem.
Cool. Yeah. You guys can like feel free and ask me the programming parts of this. I can show it to you after the lecture, but I want to keep it to math for now because there might be people here who don't know programming at all, and it'll just become confusing. Okay, so I heard a word which made me very happy. Someone said distances, and someone said shortest path when we were talking about BFS. Will anyone care to elaborate?
I mean, it's basically like layers. Each layer is a particular distance from the source. So a single vertex cannot appear on two layers. It will always appear on the layer. So we can define it like it appears on the layer which is shortest distance to the source.
Amazing, amazing, amazing. I could not have explained it better myself. Amazing. So when we had the graph, we did BFS on the graph and we got what was called a BFS tree. Let us call this layer 0. Let us call this layer 1. Let us call this layer 2. And let us call this layer 3 and so on and so forth. The source is said to be at 0 distance from itself because you're already at the point. Now, as I think others were saying, all of these vertices will be at a distance of 1 from the source. All of these will be at a distance of 2. All of these will be at a distance of 3. So if you get the BFS tree, you can get two things. The distances of all the vertices in the tree from the source and the shortest path from the source to the nodes of the graph. Agreed?
By the way, like in this, for example, if you name the points, any name, then can anything, like, can I transform this graph such that anything can be the source?
So you're saying that can instead of this being the source, can I have this being the source like that?
Yeah, yeah, yeah.
You just have to run BFS on this vertex, right?
Okay.
Right?
So like, excuse me. So using the shortest path, we are just avoiding confusion if there is a cycle, right?
Can you repeat your question? I didn't quite get what you were saying.
Like one point could be at a distance of 1 also and 2 also from the source if there exists a cycle. So in that point, we might have a confusion in the definition.
So you are saying something like S to A to B to C back to A, right? Here you're saying S
Yes.
is at a distance of 1 and S is A is at a distance of 1 and A is also at a distance of 2. Is that what you're saying?
Distance of 3, yes.
Sorry, my bad. Sorry, as at a distance of 3. Well, my response is if you run BFS from S, you will have two possible BFS trees. You can either have S to A or you can have S to B to C to A, right?
Yes.
That's a good question. 1 second. Let me just think of what you asked.
But A would also be in the first layer, right?
I think his question is like you can have two different BFS trees. This is a possible BFS tree and this is a possible BFS tree. And in this case, your distance is like 1, 2,
No,
3.
but don't we like push to all adjacent vertices before?
Excellent, excellent. I got confused, but you understood it. Right. You're right. So you're going to push A and B. This is not DFS. Sorry, I got confused myself. Right. So when you're pushing all the adjacent vertices, you're pushing A and B. So you would get this case and the layer would be 1. Devarchan, does that make sense?
Oh, yes. Yes, right.
A very good catch. That's a good question and a really good answer. I got confused there. My bad.
Sorry, I didn't understand. Can you repeat once?
Okay. So, does someone else want to answer this, like Adarsh or someone, or do you want me to explain?
No, this cycle thing.
Okay. So, if you have S to B to C to A and this, what Debarchan's question was, A is 3 distance away from S because you can go like this, but S is also 1 distance away. So how will you like ensure that you get the correct value? And a very good answer was that from S, when you do BFS, your Q will have both A and B. So both cases will be considered and this shorter case will be selected.
Okay, thank you.
Cool. So if that was all understood, awesome. So was connected components defined? Has connected
Yes.
components already been defined?
Yes.
Okay, awesome. So then, can I use BFS or DFS to find one number of connected components? Yeah, can I find the number of connected components using BFS or DFS? Any answers?
I mean, like then we will have to
Yeah,
like
we can.
first to every source, every vertex as a source, and then check how many are the same, like have the same vertex set
Interesting.
included in them.
Interesting. Interesting. Does anyone else have an answer? Mox, go on.
We can get all the connected components because basically we see every possibility in BFS and DFS. So we can just count up all the like number of connected components in each path, like in BFS's case, and we can get all the connected components.
Okay, hold on a second. Hold on a second. In this graph, there are two connected components. Do you agree with me? The first is this, and the second is this.
Yeah.
If I do BFS from S, will I be able to figure out that there are two connected components?
No, I connected components means like how many like connected graphs are there in the whole graph.
Yes, connected
Oh, I
components.
thought like from one point how many connected components, like where all we can go. That
So that means how many vertices you can visit. And in that case, your answer is right. You can visit A, Y, D. The number of vertices in the tree would be your answer. But how many connected components are there? Can you figure that out? I think Aritra was trying to.
Yeah, I was saying that like we can select a vertex and push on that, and we get a connected component, and we choose another vertex which does not belongs to that component, and we pick that and also make it source and push on that, and we could do that, and the number of times we could do that is the number of connected component in the graph.
Perfect. Absolutely perfect. So what he is saying is, let's keep an array. Okay. And I'll have all the vertices here. And for each of them, I have like either true or false. True is if it's visited, false if it's not visited. So I take like 0 and I run BFS on it. So this becomes true. So some set of these will all become true because they're all visited. So either all of them will be visited, in which case we just have one connected component, or you will have some set of vertices which are still F. Pick the first of the F and run BFS from that. Whatever else is visited, that becomes your second connected component, and keep doing that. So the idea would be for all, for all nodes, if not visited, CC equals CC plus 1 and DFS on that vertex V. Does that make sense? Does everyone see how this will give you the number of connected
What
components?
EC? Oh, connected component.
This number of connected components should define. Right? Does that make sense?
Yes.
And do you see how this can also be BFS? Both would work.
Yes. Because it essentially gives us the same set.
Correct. Just for like programmers, we usually use DFS because it's faster to implement. It's like less lines of code. So we end up using DFS, but both work. So if that was clear, okay, I'll go into this storage of graphs. Storage. Was storage of graphs covered? I don't think storage of graphs was covered. So you can store a graph in two ways. One is using a set of arrays, and the second is using a matrix. So if you have 5 vertices, you can just keep an array for each vertex, and that has all the edges to which all the vertices to which it's directly connected. Yeah, does that make sense? This is, by the way, clearly a graph.
Be there in the array of 0.
Sorry, what?
Shouldn't 3 be there in the array of 0?
Why? It's directed.
Oh, okay.
If it was undirected, you're right. If I has J, then J must have I. But this is directed, so that's not required. Does anyone else see another way in which we could store this graph? Let me give a hint. Any ideas?
Sorry, what's the question?
Can you see another way of how I can store a graph using this structure, like this matrix-like structure?
Like if two are connected, we place a 1, and if they are not connected by an edge, 0.
Very good. So if I comma j is an edge, then you just make array of I comma j equal to 1, else 0. And if it's undirected, then if a of I comma j is 1, then array of j comma I is 0, right?
Yes.
Yes.
Hear me out again. If it's undirected, aij equals 1 implies aji equals 0.
Oh no, wait, both should be 1.
Yeah, correct. This would be the case only if it's directed. In the case if it's undirected, then aij being 1 would imply aji equals 1.
Even if it's directed, if it's bidirected, then also both will be 1.
Yeah, but it's not a necessary condition. It could
Like
be.
they would be independent.
Correct. Correct. So if I have a dense graph and I have a sparse graph, a dense graph just means everything is very close together. You have a lot of vertices, you have a lot of edges between them. Second, you have a sparse graph. You have a lot of vertices and you have few edges connecting them. Which should I use in both cases and why?
I mean,
Can you
in
repeat
dense,
your question?
it would be better to use the matrix form.
Sorry, did someone ask me to repeat the question?
Yeah, I asked you.
Okay, so if you have a dense graph, would you rather want an adjacency list or matrix? If you have a sparse graph, would you rather want an adjacency list or matrix?
Wait, what are these?
Then you would want matrix.
This is adjacency list. This is adjacency matrix. My bad.
No. What's dense graph and sparse graph?
Oh, dense graph just means like you have a lot of vertices which are very close together and they have a lot of edges between them. A sparse graph means like you have like one edge, you have loads of vertices which are very far apart and there's like one edge between them, very few edges. Like sparse.
Okay.
For
Dense.
dense graph, I think matrix would be better, and sparse graph, I think the first one would be better.
Yeah. Do you have a justification for it?
Like for the dense graph, because if we write the first one, we have to write a lot more. But if we all write the matrix form, it is just 1 or 0, and like it intuitively feels more right.
Yeah, it does intuitively seem right. So does anyone want to give another answer or should I give the answer?
Also, like we can read the matrix in various forms as we like.
Sure. Yeah, I think someone else was unmuted.
In a dense graph, there would be many edges connecting each other. So in the list type, we would have a lot of edges just basically repeating again and again, or something like that. Maybe.
Repeating, why would it repeat?
Like the edges would be the list would be very huge for the dense graphs.
That is correct. That is correct. So as everyone is saying, they're right. Sparse graph is matrix, dense graph you wait what? Oh, sorry. Sparse graph you use sparse graph you use list, dense graph you use matrix. Cool. But it's interchangeable, both are fine, especially for math. Both are completely.
Aren't like adjacent list and matrix same for sparse graph?
Okay. That's a good question. And actually, no. Because if you have a matrix, do you realize you need n square computing time?
Oh, okay.
Well, in the other case, you don't. It's just you need to find the degree. That's it. Number of, and you just have to go through that. We'll be defining time complexity properly, I think, here. Yeah. And then I'll be able to explain this more conceptually. But I think we're starting to lose time, so let me go through a bit quickly. I will be starting with something very interesting called bipartite graphs. Does anyone here know what bipartite graphs are?
We can divide the graphs into like two sets such that
Yeah,
they
go.
are not connected with them. They does not have an edge with their own set.
Correct. So it just means that you can divide V into two sets, V1 and V2, such that for all vertices here and all vertices here, there is no edge between vertices of the same set. In a more practical sense, you can divide the set of vertices into two sets such that for each edge, if you color the vertices, no edge will have two vertices with the same color. Does that make sense? And then the coloring would just be the two sets. Does that make sense, or did I confuse people?
Yeah, it makes sense.
Okay, cool. So yeah, I gave you guys some thinking time now. Can you give me a condition to figure out whether a graph is bipartite or not?
Well, we know the condition. It should have no odd cycles.
Okay, yeah.
But the thing is, it was an if and only if condition, so I don't know how to prove it.
Yeah,
The first part is easy. The second part.
Can we prove using the chromatic numbers?
Yeah, you can. Chromatic numbers is the most straightforward proof, or at least it is one of the other proofs, but I'll be going over a comp science proof of it. So consider a bipartite graph. If I run BFS on a bipartite graph, I'm going to get something like this. Can I just color all of this red, color all of this red, and color all of this
Odd
blue?
layers and even layers.
Exactly. Each odd layer is of the same color, say red, and all even layers are of the same color, say blue. And that's just how it's going to be bipartite. This is how you can color a bipartite graph. I've still not proven that if it's bipartite, if and only if it has no odd length cycles, right? I think I'll attach the proof of that as like a note, because I don't want to go over that proof right now. I just want to cover the algorithms, like the algorithms. Is that okay?
Yes.
That one to work quickly. So yes, we can finally go into something quite interesting. Trees. Wow. So I said BFS tree, DFS tree, this tree, that tree. What exactly is a tree? A tree is a connected acyclic graph. That's it. Okay, a tree is a connected acyclic graph. That's all we're actually going to go. We're just going to go into this depth for trees, because if you want to study tree diameter, tree matchings, there's so much you can go into it. But I just want to cover graphs on a whole. So this is just a type of graphs in which it's connected and acyclic. Okay. I'll just cover one question regarding trees. Given a tree T, how can I find the furthest node from you. We were talking about shortest paths, but longest paths should also be something, right? What's the worst possible way in which I can do it? So yeah, what is the furthest vertex from you? How can you find that? This is an interesting question.
But why do we care of this?
Why do we care about this? It's a good question. That's a very good question. Okay, so if you wanted to perhaps, like, in many comparative programming problems, if you want to find out something which is called tree diameter, you end up using this, because what happens in comparative programming problems is you have like two trees, say T1 and T2, and you have to minimize the furthest possible distance by removing two vertices or something. In these cases, you have to find what the maximum distance is because you want to minimize it. Does that make sense?
Okay, yes.
So do you have an idea on how we can find the farthest node?
Also,
BFS
just a small
brute
comment.
force.
A lot of like these graph things you can think about as like Facebook connections. And in that sense, like you can make sense out of these, like, okay, two vertices are connected if and only if they're like friends. And you want to find out, okay, like we have some network, then which two are the farthest place? Maybe something along that side.
That's a great analogy.
The last layer in the BFS/DFS.
Interesting.
Wait, how are you applying like the same two different algorithms on the same graph? Will it just not give the same?
Sorry, what?
Yeah,
You were saying something. What did you say?
I'm asking that. Can you apply two different algorithms on the same graph? Like, wow, how will it help if we do?
And it just, yeah, it doesn't help unless, yeah, it doesn't help. So I don't know, like, why are you asking that? Like, what's the reasoning behind that? We're not applying the same algorithm here, two different algorithms here.
Oh no, I thought others said first BFS then DFS.
You meant
to find
BFS or DFS and find the last layer.
Because both are basically the same for a tree.
Okay. So this does not work. 1 second. I just need to think for a second. Give me a second. Yeah. So let me give you a tree. Yes, yeah, this is why it doesn't work. Yeah, this actually does not work. So the reason is you can have something which we tend to call a split, where you have it going in this direction for some time, and then the DFS traversal ends. But because this was already visited, you can have something like this, where this vertex is already visited, but you need it in your path to make it longer. I can give a proper counterexample of this. I have it. I can give it to you for why this doesn't work. Okay, just I can activate. Let me derive it right now. Just give me a second. 1 second. I have it saved. 1 second. Right. Okay. Sorry. This answer is correct. The question I asked was inaccurate. I'm sorry. So if you want to find the furthest node from a node U, this is correct. I'm sorry, this is correct. What I meant to ask was, if you want to find the furthest possible distance between any two nodes, what can you do? So yeah, Adarsh, your answer was right. My bad. For this case, your answer is correct. My question is, given a tree, what is max of distance of u comma v for all u comma v belonging to capital? Yeah, that's my question.
We can do it for like we can do the layers thing for all vertices, and the maximum possible layer would be the maximum distance between U and V.
That works, but unfortunately,
We can reduce the number of points we need to do that on. Basically, the only vertices we need to do that on are the vertices which have only one connected component with the other, like only one connected vertex directly connected.
these are all correct answers and they will work, but it's not optimum. It's not like you can do it in a better way. And the answer is actually by doing DFS multiple times. But you should think more about it. From where can I do it? Just take a minute.
From all the leaves.
From all the leaves is again, yeah. I'm going to say you can do it in 2 DFSs. Irrespective of how big slash small the graph is, you can do it with DFS only twice. Can someone figure out how I can do it? Okay, I'm going to give the answer, but not the proof. The proof is like a homework exercise. Okay. So the answer is DFS on U, where U is an arbitrary vertex. Check the DFS tree and find the farthest V. Now DFS on V. Find the farthest CZ. Answer is equal to dash. I'm going to leave this as a homework exercise. Unless you want to answer. Does anyone want to answer?
Is it just UZ?
That's what I think. And yeah, UZ is correct. But the proof of this is quite interesting. I'll leave it as an exercise. And you can like either DM it to me or like put it on OMC and I'll respond to whatever your proof is.
I think it would be V to Z, right?
Oh,
Because yes, if we have a star graph, then U to Z will become 1 if we just take the center, but V to Z will give 2.
interesting. I'm not going to give the answer of this. This is quite an interesting logic puzzle as well as mathy. So, you know what? Let's just put the third option as well, U to V. Max of all of these. I don't know. Let's put all the possible options. If any of you get an answer for this question with proof, put it on OMC and like the first person who gets it, he will get a, I don't know,
It's
congrats.
just like because since it's a tree, we can't have cycles. So the only way to move from U to Z would be to go through V.
Excellent answer. Excellent answer. That's a very, very good answer. So Bearav, yeah, this is such a good answer that I'm going to say it now. Bearav's point was, here it's just going to be 1, and then I'm going to get something which is 2. But Bearav, B to D, this path of 2 will encompass A as well. So your paths, it's not looking for, once again, you're not looking for the furthest path from A node. You're looking for the furthest possible path. So yeah, this is just a giveaway. The answer is U to Z, but I am looking forward to seeing you guys as proofs. So I think this ends the first part of our lecture. Now we will be going over, okay, I already did trees. Yeah, asymptotic notation. Very nice. So we spoke a lot about what optimum is, what good is, what the best is, but I haven't formally defined any of that. So let's go ahead and do it. I'm trying to find a nice color. Okay. Okay. I have two functions, f of x and g of x, and some constant value c, after which f of x is like always greater than g of x. Okay. Just assume you have this situation. Before that, you can have anything. It can be before, smaller, anything. But there's some point at which they intersect, after which f of x is like larger than g of x. Okay. Here we say that f of x is equal to big O of g of x. This big O means loosely upper bound. Okay. Is the definition clear? I'll explain its uses and everything later.
Yes.
Now, you know what? I'll explain the second one here. Do you see that g of x is like lower, f of x is lower bounded by g of x after this point? So we say that g of x is omega of f of x. Omega means, big omega means lower boundary. And then you have this third case, where you have this graph, which is permanently between these two graphs. This is not actually two different functions. It's the function g of x multiplied by a constant c1 for this value and c2 for this value, where c1 and c2 are both positive. So you see how f of x is sandwiched between these two? In this case, we say that theta means tight bound. And if you have that something is theta of n, then it means it's also O of n and omega of n. Sorry, someone asked, I didn't understand the question, which was just DM'd to me. Can you maybe type it in again or speak up? Both are fine. Just give me a second. You can retype your question. I didn't quite understand. What do you mean this? Big O is the upper bound, big omega is the lower bound, and theta is the tight bound.
What exactly do you mean by tight bound?
Tight bound means that, okay, let me actually give the formal definition. So you have a function f of x, you have a function g of x, and you have constants c1 and c2. So I'm saying that for c1 times g of x and c2 times g of x, f of x is always going to be between these two after some point. After some point c, this is always going to be true.
Oh, okay.
It's sandwiched between that. And one second, let me answer the question. Yeah, what you said is correct. So did I make a mistake?
I think the graph is mistaken.
C1 times g of x is less than equal to f of x is less than equal to c2 times g of x. Is there a mistake?
No, and the lower graph for O of g of x.
Here?
Yes.
Oh, okay, right. Okay. So f of x is the one which is the upper bound, right? You're right. You're right. F of x is the one which is the upper bound here. So it would be that g of x is upper bounded by f of x. Yeah, that's what you're saying, right? Yeah, sorry, my bad. So the one which is the upper bound comes inside the big O notation because that's the like worst case scenario. And this is the function that we're analyzing basically. So do you want me to give the formal definition or does this just clarify it completely? Because in the case where it's like big omega, this would just not exist. And in the case where it's omega, this would not exist.
Yeah,
And in the
that,
case of theta, both would exist. So does that make sense?
yes.
So I'm just going to explain the utilization of this. So this is a bit comp science, but like there's not really much comp science in this. So if you read this, it would print high how many times? Arranged just means that many times, by the way. And nested means that for each of these, this will happen that. For each I, this will happen j times. That's what it means. It's an application of
Start from
N times n minus 1.
exactly. To be n times n minus 1, which is n square minus n. Now, this is where we'll use asymptotic notation. N squared minus n is upper bounded by n squared, right? This means that n squared is big O of n squared minus n. So this algorithm has a runtime of O of n squared. At most, it can be n squared. Does that make sense?
Yes.
Instead of n minus 1, if I made this n, then it would be big O of n squared and omega of n squared. So then it would be theta of n squared, right? Now,
Yes.
just some properties about this. If you have 2n squared, that's actually the same as n squared. You can drop the coefficient because if you see this, C1 and C2, these constants are something that you can actually choose on your own. This, if the graph is like this, also you're fine. If you have this, or if you have this, as long as it's bounded, you're okay. So 2n square, asymptotically, 2n square is equal to 3n square is equal to 4n square is all over n square. But if you have n times n squared, which is n cubed, then obviously this is not over n squared. Did that make sense? Asymptotically by the means as you
Yes.
go larger and larger, like towards infinity, limit tends infinity. Does that make sense? Because the 2 factor is irrelevant, right? When n becomes huge, 2 is irrelevant.
Yes.
So I hope asymptotic notation was clear. So I'll just go.
N cube should be inside the O, right?
Sorry, what?
Shouldn't n cube be inside O?
Yeah, I meant O of n cubed is not equal to O of n squared, right? So can someone give me the runtime of this? Also, please DM me the answer for your runtime of this. Don't say it aloud, just send it in a message to me because I want to do this in a specific way. So everyone, please DM me the runtime of this code. Runtime is just what we discussed, the O of something. So this is a code snippet to find out 2 to the power of n. What it does is, if n is 0, it will return 1. Otherwise, what it will do is returns p of n minus 1 plus p of n minus 1. So if it was like, if I plug in n equals 3, it will say, let me put p of 2 plus p of 2, which is just 8. Because it will be p of 1 plus p of 1 plus p of 1. P of 1 times 4, basically. So it would be 8. Right? So does the algorithm make sense?
Yes.
Okay, I'll already start. Okay. Any other answers? I've got only 2 answers so far, guys. Just even if you're not 100% sure, just feel free to answer. Okay, so I've got 3 different answers. I've got n squared, I've got I've got 4 answers. I've got n log n, and I've got 2 to the n. These are the 4 answers that I have got. So first of all, I have no idea where these two come from. So like these two are just, I'm not sure where these come from, but n squared and n do seem to make sense because like n squared, it just seems to make sense because actually n squared also does not make sense. N is the only one which actually seems to make sense here, right? Because what you're saying is if I want 2 to the power of 3, I need to compute 2 to the power of 2, I need to compute 2 to the power of 1, I need to compute 2 to the power of 0. So that will be n iterations. So the people who answered O of n, was this the reasoning behind your answer? You can DM it to me or speak aloud now. Okay, yes, yeah. I'm very interested in the people who said 2 to the n. Can you care to give a justification? I think there were 2 people who said it's 2 to the n, Adarsh and Bhairav. So could you tell why you think it's 2 to the n? Bhairav.
Well, if you take n and it calls it for n minus 1 twice, so it takes at least as much time as twice the time that n minus 1 took. So it has to be at least 2 to the n. And then the other constants go away pretty much.
You're telling me that this simple code is taking exponential time.
Yes.
Okay, does anyone agree with what he said?
And in fact, I implemented it some
Okay.
time ago.
Does anyone agree with what he said?
Mine was kind of the same reason.
Yeah, I saw your answer, but you agree it's 2 to the n, right? Not 2 to the n plus 1, because the constant factor, it's like 2 to the n plus c.
Yes.
This constant is just very small, so it's removed. So I'll explain why it's 2 to the n. So the answer is actually 2 to the n. So what happens is, if I plug in n, I need to find p of n minus 1 and p of n minus 1. I need to find p of n minus 2 and p of n minus 2. I need to find p of n minus 2 and p of n minus 2. Do you realize that this is going to be a complete binary tree? And for each iteration, I actually need 2 more times. So if I was at layer x, which had me doing n operations, then layer x plus 1 will have me doing 2 times n operations, and x plus 2 will have me doing 4 times n operations, and so on and so forth. So the complexity ends up being 2 to the n. Does that make sense?
Shouldn't it be 2 to the power n minus 1?
Yeah, that's what I'm just, the math is just, it's O of 2 to the n. The fact that we now know bigger notation, 2 to the n minus 1, 2 to the n plus 1, everything is the same. It's all 2 to the n. Could you please repeat once? Sure. So let me do it with an example. So suppose I wanted to find P of 4. Then my algorithm says, if n is 0, which is not true, so you have to go to else. So return P of n minus 1 plus P of n minus 1. So it will do P of n minus 1, which is P of 3. And then it will find P of 3 again. Then it will find P of 2. 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 It will find P of 1, P of 1, P of 1, P of 1. Okay, I don't know how to copy, but yeah. So do you realize that it ended up doing 8 operations here, 4 operations here, 2 here, 1 here, which is I think 2 to the power of n minus 1, which is what I think Aritra was saying. So yeah, 2 to the power of n minus 1 is correct. But do you realize how it continuously calculates the same thing over and over again?
Yes.
This is why it's 2 to the power of n, which is exponential. The person who asked me to repeat, does it make sense? You can either DM or speak up, both work.
Yes.
Okay, cool. Let me give another algorithm.
Is there like no way we can, instead of making the same thing be counted those many times, make it just count once and make the answer n minus 1 or something?
You can. I'll get to that in a second. But how about this algorithm? How about this? This is O of n, right?
This is this, yes, O of n.
Is this O of n?
Yes.
I'm just waiting for others to answer. Like you can DM or speak up. Do you guys think it's O of n? Yeah. So this is one way of doing it. The other way of doing it is we keep like an array which just stores the values. So like we say P, it stores P of I for all values. So when you compute the value, you store it here. You just store it, and then instead of computing again, you just call P of I, if that makes sense. This is something called DP, and it's very useful in computative programming. The basic idea is that instead of recalculating the same thing over and over again, you just store the value and then call that value, which changes your time from O of 2 to the n to O of n, which is amazing. That's a huge change. But does this make sense to everybody?
Yes.
So we covered BFS, DFS, trees, bipartite matching, connected components, and basically everything you can do with BFS and DFS. So there are two more algorithms like Dijkstra and topological sort, but it's already like almost 8:30. So do you guys want me to continue or should we call it a day? I have
Continue.
continue. Is everyone okay with me continue?
Yes.
Okay, cool. So just what I'm going to cover, yeah. Okay. So, okay, yeah, no problem. If you have a class, you can absolutely leave. No problem. You can watch the recording later. Actually, should I continue, Sai, or should we call it a day?
Or
Should
maybe
we?
also like take one more lecture.
Yeah, that's also an option. Sai, what do you say? Like, I have no problem continuing.
We can do that, or we can, yeah, I think if people are fine with continuing, it's fine. We can continue.
I just think like a lot of people have left. So do you want me to continue or just do it another day? Both work with me. Because like I think the intended class time was 8:30, so people might have other commitments after this.
That's true. Yeah. Okay, so let's do it another day then. I think have, like around half the people are left.
Yeah.
So okay.
Okay, guys.
Thank you so much.
Yes,
Yeah.
I go.
This was a really fun class.
Thank you.
Yay.
A
I
lot of
agree.
interesting algorithms like topological sort, Dijkstra. This is just the basics. But those go into like a lot more coding style. Like you have, it's a lot more CS related. This is the mathy stuff. So I hope this was a fun lecture and you guys learned a lot.
One thing you can do is maybe put up some material that people can go through so that they're more comfortable with some CS stuff. Like it doesn't have to be material made by dudes, like Wikipedia articles or something along those lines. People can go through that and maybe we can have a more CSE lecture next time. I think some people I definitely see are interested in that.
Yeah, sure. Absolutely. So are there any questions related to graph theory or CS in general? I'm not an expert, but Sai is, so she can answer all your questions.
No,
Okay, yeah, but if you have any questions, like feel free to speak up now, or you can always DM me. Okay, I think people are starting to leave now. So, okay, then this ends the lecture for today. I hope all your doubts were cleared and you guys had a new outlook to how graphs can be studied from a CS point of view. Thank you. Yeah, I hope you had fun. It was fun for me as well.
Thank you.
Thank you very much. Bye.
Thank you. Bye.
thank you. Bye.